this video about the line of best fit in linear regression. By the end of this video, you should be able to choose the line of best fit for a given set of data. You should be able to interpret the slope and y-intercept of a line, and you should be able to use Desmos to write the linear regression equation. Alright, so let's look at a line of best fit. A line of best fit is a line that best bisects the data in half. So we want approximately half of the data points above the line and about half of them below the line. So this line is used to make predictions about data values that aren't there. Well, what if somebody, so we have 35-year-olds and 40-year-olds, what if somebody was 37? We can make a prediction about the resting heart rate based off that age using the line of best fit. So what we want to do is we want to be able to match which of these lines best approximates this. So because our lines are in slope-intercept form, what we want to do first is we want to look, we're going to compare their y-intercepts, and we're going to compare their slopes. If you notice, I'm going to just kind of write that in there. I'm approximating the center. Okay, I was trying to get about half of the points above the line, about half of them below. That's a negative slope. So when I look on here, this A has a positive slope. It cannot be A because of the positive slope. The other three lines here are showing a negative slope. So once I've checked for the slope direction, I'm going to go back and look at the y-intercepts and see if I can eliminate anything. So this, I kind of came in about 70, and that was just my best guess. I have a y-intercept at 74, 80, and 50. Only one of those is close to where I came in. That's the 74. So this has to be the line of best fit for us. Okay, so it's a matter of matching, eliminate any choices based off the direction, positive or negative, and then check out your y-intercepts. If that doesn't help you, then we're going to count slope. So let's try that with this next one. So we have here a negative sloping data set. It goes down from left to right. So I'm going to look, this has a positive slope, so it can't be this. This one also has a positive slope, so it cannot be that choice. So now what we're going to do is we're going to look at the y-intercepts, and I notice that they're both -2. So that didn't help me either. So the last step is we're going to count these two slopes here. Remember, so this is negative, so this says go down 3 and then right 5. This one says go down 5 and then right 3. So just count it out a couple times and see which follows the data. So let's try down 3, right 5. So I'm going to use this y-intercept, the -2. I'm going to go down 1, 2, 3, and right 5. 1, 2, 3, 4, 5. That puts me out here. Let me kind of like, what if I went opposite? 1, 2, 3, 1, 2, 3, 4. Neither one of those is in this data. You see how it's on the outside? Let's try counting the other one to see if it's any better. So this one says go down 5. 1, 2, 3, 4, 5. We're off the chart, and then right 3. 1, 2, 3. That would go there. Let's try it the opposite way. 1, 2, 3, 4, 5. 1, 2. Do you see how those are more in line with the data set? So this is going to be our line of best fit if given the choice of only those 4. Okay, let's try it again. We're going to look at the slopes, eliminate what we can, look at the y-intercepts, and then count the actual slope out to see which one fits best. Okay, so we have a positive slope here. This guy has a negative slope, so it cannot be him. Positive, positive, and that one's negative. So we're going to eliminate those two because they are not possible because their slope has the wrong direction. I'm noticing that both of these say go through at 3. Here's where the y-intercept is. So I'm just going to count the slopes again. So this one has a slope of 2. Remember, it's really 2 over 1. So it's a positive 2. So you're going to go up 2 and right 1. So from our y-intercept right there, go up 2, right 1. Up 2, right 1. I'm going to try it the opposite way. 1, 2 down, left 1. 1, 2, left 1. That's pretty in there. I'm going to go take a look at the other one just to be sure. This has a slope of 1/2. So from my y-intercept of 3, up 1, right 1, 2, 3, up on one. See, you're already all the way out of the data set. Down one, left one, 2, 3, down one. So that line would have been much flatter, and that's not what this data is going to do. So our best choice here was this one. All right, now our last one, he's a little trickier because these answers are not in slope-intercept form. So we're going to convert them. We could also use Desmos to put these on the graph and go see which one fits best. But I'm going to convert these, so I'm going to pause the video and come back with these converted into slope-intercept form. Alright, so this is what we've done multiple times in the past. I isolated the y variable, so like I moved the 2x and then divided everything by 3. Moved the 3x, divided everything by 2, and I rearranged these to each be in slope-intercept form. Looking at our data from left to right, this is a positive slope. This line has a negative slope. That line has a positive slope, so it could be that. This line has a negative slope, so it can't be that. And this line has a positive slope, so it could be that. I'm noticing they both have the same y-intercept, so again, we're going to count the slopes. I'm going to start with this one. I'm going to start down here at negative 4. 1, 2, 3, 4. And it says rise 2 and run 3. Rise 2, run 1, 2, 3. Rise 2, run 1, 2, 3. It's feeling a little flat. Let's see what happens if we go the other direction. Down 2 and left 1, 2, 3. So that line would go like that. That's not really going through the middle of our data. So let's count the other one and see what happens. This one says rise 3 and run 2. So from that same starting part, rise 3, 1, 2, 3, run 2. 1, 2, 3, run 2. You see how it's right in the middle. 1, 2, 3, 1, 2. And if I draw that line, I'm more in the middle of the data. So this is going to be the choice of the line of the best fit. So you really want to look at the slope, the y-intercepts, and then count the slope if necessary, because you want the line that goes best into the middle of it. All right, let's look at what we got to do to calculate the line of best fit. So if you're given a set of data, so before we only had the graphs, but if you're actually given the points, we can calculate the line of best fit and then use that resulting equation to make predictions. We're going to use Desmos to help us make the most precise line of best fit. When we make our line, we're usually going to write it in slope-intercept form. Y equals mx plus b. M is the slope and b is the y-intercept. We've talked about this before too. One thing that we are going to be doing is we're going to interpreting what does this slope mean in the context of the problem, and what does this y-intercept mean in the context of the problem. So in general, when we're talking about slope, slope is for each single unit increase in the x context. So every time x goes up by 1, what happens to y? There will be an average either increase or decrease. It will be an increase if your slope is positive. It will be a decrease if your slope is negative in whatever y values we're talking about. For our y-intercept, that is whenever our x context is 0. So whatever our x context is, when it is 0, we will have an expected y context of whatever the y-intercept is. So we'll get a chance to interpret some here. Now these instructions are the same as from the correlation instructions. They end up being in the same screen. So you need to stop the video, go to Desmos Georgia Testing Calculator, and we're going to input this set of data. Alright, so I have entered the data. Usually you can see the data points be plotted on here. I'd have to scroll way out. There we go. Now we can see it. There's our data right there. Okay. To get our equation, we're going to do the same thing, same steps as when we were trying to find our correlations. Click in the box below, and you'll notice our table was named x1, y1. So when we use our notation, we need to be sure to use x1, y1. So we're going to say y1, and then your tilde, which is going for equals, but we can't use equals, mx1 plus b. Now all of the instructions on typing that in are above this problem on your worksheet. So if you're having trouble following along, All of your instructions on how to type it in are right here on the worksheet. Okay, so we've taken this. Now we're going to write the equation of the line of best fit. So let's go back and look at this. Previously, when we found correlation's right here at R, and it tells us it's got a negative correlation. It's very close to 1, so it's very strong. And then down here it says parameters, and it says M equals and B equals. That's to plug into your equation for your line. Okay, so let's take a look at how we're going to plug this in. So we are plugging into slope-intercept form of y equals mx plus b. Okay, so we're going to write y equals. Now the m value, if you go back and you look, the m value is negative 1.07167. I'm not going to use the whole thing. I think I'm going to go about 2 decimal places out, so negative 1.07. So m x, and then I need to go back and I need to look and get what the b value was and plug that in here. 92.86, I'm going to call that 92.9, and it's a positive number, so I'm going to say plus 92.9. This is our regression line. This is our line of best fit. Okay. From this, we can answer some different questions. First, let's review what was the correlation coefficient. Is it strong or weak, positive or negative? Okay. So our correlation coefficient, remember, is right here with R. And our R equaled negative 0.9396. So negative 0.9693. Okay. Negative 9693. I'm going to make sure we have the right one. Now, this is strong or weak. Remember, the strongness or the weakness doesn't have to do with this, the negative sign. That has to do with the direction the data is going. Is it sloping down or sloping up? Ours was sloping down. But the closer to 1, whether it's positive or negative, this is very strong. It's close to negative 1, and it's negative. Okay? So we're going to interpret the slope. So remember up above, slope was for every time x increases by 1. So our x value is degrees latitude. So for each additional degree latitude, because that's our x values represented by degree latitude, there is an average decrease, because we have a negative slope, an average decrease in temperature of 1.07 degrees Fahrenheit. Okay, so each time the x value increases by 1, so our x values were degrees latitude, so for each additional degree in latitude, then the second part of that says there's an average either increase or decrease of whatever the y is. There is an average, we had decrease because we have a negative slope, in temperature, because our y values are temperature, of whatever the slope is, 1.07 degrees Fahrenheit. Now we're going to try the y-intercept. The y-intercept right up here is when whatever the x context is 0, what's the expected y value? Okay, so this is our x context is latitude. When at 0 degrees latitude, the expected temperature is, well, what's your y-intercept? Your y-intercept was 92.9 degrees Fahrenheit. When you have whatever your x is 0, that's the y-intercept. That's all the way back over on your axis. What is the temperature there? 92.9. Now we're going to use our line. Estimate the average temperature for a city with a latitude of 48 degrees. Well, latitude is an x value. So that means we need to take 48 and plug it in where the x is. So we're going to say y equals negative 1.07, and instead of x, we have 48 plus 92.9. From here, you need to get your calculator out, and you can put it straight in. You don't put in the y equals, but negative 1.07. So pause the video and get that on your calculator. So when you run this through, you should get 41.54, and this is degrees Fahrenheit. So when you're at 48 degrees latitude, this 48 degrees is not a temperature, it's an angle. 48 degrees latitude, the temperature is expected to be 41.54 degrees Fahrenheit. Okay, let's try this again on the next page. All right, since we have the Olympics coming up, we have an example related to the Olympics. So the data in the tables below shows the 500-meter gold medal speed skating times. Then it says use 1980 as 0. So we don't want to use these as our x values. They're way far away from the y-intercept. It says make 1980 0. And then we're going to go years since. 1984 is 4 years since 1980, so we're going to say that's 4. 1988 is 8 years since 1980, so this is going to be 8. 92 is 12 years. 1994 is 14 years, sorry. And 1998 is 18 years. Okay, so what I want you to do is I want you to pause the video. I want you to input this data, but you're not putting these years in. For the x values, you're going to put 0, 4, 8, 12, 14, 18 for your x's. And then your y values will be these times. See if you can find your regression line and write it, and your correlation, and then come back to see how you did. All right, so I've moved my screen so we can see these data points. All right, they're way up here. They're all the way up to 400 on the y-axis, so I just scroll a little bit to get to them. And so we can see the green line is the line of best fit. When I come over here, I have my numbers, I have my correlation, and then I have my slope, and I have my y-intercept, which will give you the following equation. So you might have rounded it a little bit differently than me, but I got y equals negative 2.29x plus 430.7 should be your equation. Your correlation coefficient was negative 0.8108. It is strong and negative. Now let's go ahead and interpret the slope of the regression line. That means every time x increases by 1. So this says for each additional year, because we're talking about years, for each additional year, what's going to happen? There is a predicted, because this is like a magic 8-ball, it's a prediction. Predicted, our slope is negative, decrease in time of 2.29 seconds. So it's an average predicted decrease in time, 2.29 seconds for every year. Okay? Then our y value, see if we had gone and we would have been almost 2,000 away from the y-intercept. That's why we didn't do that. We adjusted it, so we said make x 1980 0, so that's your y-intercept, and then we can go every 4 years there. So in 1980, because that's when x would have been 0, the expected time, so it's like speed skating time, we put our context in there, was your y-intercept of 430.7. Now we actually have a y-intercept. That's what's observed. This is what's predicted. It's not necessarily going to be the same thing. Now, estimate the 500-meter time for the 2022 Olympics. That's what's coming up. So we're going to estimate this time now. So 2022 is a year. Years are x values. But remember, our x values are years since 1980. So 2022 minus 1980 gave me 42 years. It's been 42 years since this original time. So that's going to be your x value that we're going to plug in because we're doing years since 1980. So we're going to say y equals negative 2.29 times 42 plus 430.7. I just took it and plugged it into the equation for x because we were asking about an x value. And you should get a time, because time are y values, of 334.52 seconds. It'll be interesting to see how close we are with that. All right, one last example. What I want you to do is I want you to put everything in the calculator. You don't need to adjust. There's no years since, so we're going to do that. Put this in the calculator and generate your regression line. So I put the data in. You can see the points were graphed for me, and I generated the line that runs through the points. Look at the correlation coefficient. Look how close to positive 1 it is, because those are all very much in a row. Now, I didn't need the correlation coefficient. I wanted us to write the lines. Our slope and y-intercept are kind of gross. They are decimals, but that's okay. So we ended up with a y equals 0.14x minus 0.25. I just rounded them to 2 decimal places. The question that we're being asked is, Sam is the same height as the people in this group. If he has a BMI of 25, estimate his age. Well, let's take a look. The BMI is a y value. So they're saying, what if he has a BMI of 25? We're wanting to know, how old is he? So because they gave us a number that's the y number, we're going to plug it into the y spot. So we're going to say 25 equals, because that's a y value, 0.14x minus 0.25. So now it turns into algebra where we need to solve for our variable x. Anytime we want to isolate, it needs to be the only term on the single side. So we're going to add 0.25 to both sides of the equations. Oops, sorry, let's fix that. This is plus 0.25 and I had written minus 0.25, so we want to make sure we're doing the right math here. Okay. All right, so this is plus, so we're subtracting it. These cancel out, that's why we did that. 25 minus 0.25 is 24.75 equals 0.14x. Now to get x alone, we're going to divide both sides by 0.14. And I get x equals 176.8. And in the context of our problem, that's his weight. So that's going to be, Sam weighs approximately 176.8 pounds. Right, so hopefully that was helpful. I'll see you in class.